I want to look at more about triangular matrices and diagonal matrix. So let's take the determinant of this upper triangular matrix, and we're going to expand on the first column each time. So block out the first row or column and first row, and then you're left with this determinant. So it's 1 times the determinant, and then etc. And if you simplify it, you get 1 times -2 times -1. Now that actually is the product of the diagonals, like that. Basically everything else zeroes out. So that is a property, actually. That's not a fluke. So, so what you get is the product of the diagonals. So example 4 on page 255 is a general concept in the basic proof of it. So for an upper triangular, lower triangular, or diagonal matrix, the determinant is the product of the diagonals, which is a nice result. So in general, it would be like this, as I highlighted here. You end up getting just that product. So next we're going to look at number of properties. So let A and B be square matrices. So both square, I think I restated it here, but oh well. So the determinant of A is equal to the determinant of A transpose. And they'll prove this stuff. I didn't go through the details of the proofs. Try to just give you an idea why it makes sense in most cases. They do the proof by induction. We'll talk more about that probably later, but not right now. So they assume it's true for finite number, like n is equal to 1 or 2, and then you assume it's true in that case for everything up to n or less than n, and then they do the rest of the proof by induction. So you want to read that, but it's not something I'm going to hold you to right now. So I just did a couple examples, right? So if you have A and its transpose, then you get -2 in both cases. Now, the idea is it's basically the same matrix, and you already know that you can expand on any row or column. So it's essentially that kind of comes from that idea. Property 2, interchanging 2 rows of A to get B. So you interchange the rows. Then they're opposites, and one's negative of the other. So I showed an example here, right? And you get 2 opposites. Again, the proof is page 256 by induction. So you need to remember the properties, what they're saying. So these are all the elementary row operations for matrices: interchanging 2 rows, multiplying by a scalar, multiplying by a scalar and adding it to a row, that kind of concept. Property 3, if 2 rows of a matrix A are equal, then the determinant is 0. This one I did go through the proof because it's kind of simple. So let's let B be a matrix obtained by interchanging the 2 equal rows of A. So now we're going back to property 2. So 2 rows are the same. So let's just suppose you interchange those 2 rows. So by doing so, we get that the determinant of B is equal to negative the determinant of A. But however, if you interchange those same 2 rows, you still have B is equal to A. So the determinant of A is equal to negative the determinant of A. So the only way you can have equality of 2 things and be opposites is if what? Is if that determinant is 0. Okay, so it gives you a way to also do determinants. If you see 2 rows that are the same, then you know the determinant is 0. Property 4, if a single row of a square matrix is multiplied by a constant, scalar, to get a matrix, then basically it factors out. But it's just a single row. There's another property, which I don't think I listed here somewhere, but let's just call it property for B. We'll call this one A. If you multiply a matrix, so like if you have A, and you have, so R times A, and you take that determinant, then it comes out with the power. So whatever the size of the matrix is, that's the power of the constant. So it's basically applying property for A multiple, to each row. Okay, so keep that in mind. We use that later, not in this video. Property 5, the product of one row is added to another row. The determinant of the resulting matrix is the same. Okay, so that's, but the proofs are, I wouldn't say complicated, but they're tedious to go through them. So not something I want to look at like for exams and stuff, but you may want to take a look just to see how they're done. Okay, so that's page 258. Maybe we'll come back to it another time. Okay, then so property 5, I was just describing this, what we just did. So property 5 concludes the effect elementary row operations have on a determinant of a matrix. So you need to be aware of all of those properties as we do stuff. The next one has to do with theorem 4.3. So this is a sketch of a proof, basically. Suppose we reduce A. So you have a matrix A, right? Reduce A to echelon form. But do that without scaling, like without multiplying by like a fraction. So you don't want necessarily the diagonals to be 1 or anything. Right, so just reduce it without scaling it or multiplying by constants. Then what you get is the determinant of A is equal to plus or minus the determinant of H. So if you interchange rows, you might get opposites, but they're equal. That's because of all the properties we just showed above. All right, and then the determinant of H, because it's in row echelon form, reduced row echelon form, right? It is a diagonal matrix. So the determinant of H, it could just be upward triangular, it doesn't matter, is a product of its diagonals. So we also know that H has all non-zero entries on its diagonal if and only if A is invertible. Right? You don't get that pivot to zero out. If you get a pivot to zero out, then it's not invertible, and vice versa, right? So then that brings us to this. The determinant of A is non-zero if and only if A is invertible. And then we can talk about singular as well in there too. So the theorem states that. Theorem 4.3 states, so singular means it's not invertible. So it's a singular matrix, which means it's not invertible, if and only if the determinant of A is equal to 0, which basically means you get a pivot to 0 out, right? You get a row to 0 out. Or you can state it like I stated above, A is invertible if and only if the determinant of A is non-zero. So non-zero determinant means that A is invertible. It's an easy way to check to see if you're going to get a unique solution. Then theorem 4.4, determinant of A is equal to determinant of A times determinant of B. So this I have a sketch of the proof to go over. I'll probably go over that in the next video. So just get going on these properties, and then we're really only going to do a couple things in 4.3, just some basic calculations, and we'll go over Cramer's rule again, and in case you had not seen that before, but nothing real advanced in 4.3. So focus on all of these. and you're good to go. Then we'll get into chapter 5. So we'll spend a good amount of time in chapter 5 calculating eigenvalues and eigenvectors, which is an important topic.